Close your eyes for a moment. Forget the world outside your window. Let's travel, you and I, to a place of profound silence and ancient violence. A place where planets go to die before they are even born. We are floating now in the deep, sun-dappled darkness between the orbit of Mars and the mighty Jupiter. All around us, tumbling in a slow-motion ballet older than life itself, are millions of frozen fragments. Stones the size of cities, mountains of pure metal, icy primordial snowballs darker than coal. This is the asteroid belt, and everything you think you know about it is wrong. This isn't just some rubble-filled highway. This is a crime scene, a cosmic murder mystery 4.5 billion years in the making. The victim? An entire world that never got the chance to be. The prime suspect? A gravitational giant with a turbulent past. And the clues are scattered literally everywhere, in every rock, every speck of dust. Tonight, we are detectives of deep time. We're going to piece together this epic story of creation, destruction, and cosmic theft to answer one haunting question. Why is there nothing here, when by all the laws of the universe, there should be everything? Wherever you are in the world right now, whether you're under a blanket of stars or a ceiling of clouds, take a second to feel the scale of this. We are on a pale blue dot, contemplating the fate of a world that could have been our neighbor. It's humbling. It connects us. The visuals will paint the picture, but let your mind wander. If you drift off into the cosmos, that's perfect. Sometimes the biggest ideas take root when we're not forcing them. If these journeys into the heart of scientific wonder bring you a sense of peace and awe, I have a small request. If you'd consider subscribing and giving this video a like, it would mean the world. It's more than a click. It's a signal to the algorithm that there are more curious minds like yours out there, hungry for understanding. It allows me to keep doing this, to keep unraveling these cosmic stories for you. Your support is the fuel for this ship. Picture our solar system from a God's eye view. You see the inner planets? Mercury, Venus, Earth, Mars, clustered close to the sun's warmth. Then, a gap. An expanse of space so vast it stretches over hundreds of millions of kilometers of seeming nothingness before you reach the majestic gas giants. But that gap is an illusion. It is not empty. It is populated. Not by a world, but by the ghosts of one. Countless fragments of rock and metal, from pebbles to dwarf planets, tumble in silent, elliptical orbits. This is the main asteroid belt, and its very existence is the first great clue. According to all the rules of how solar systems form, that region should hold a planet, perhaps a substantial one, maybe even as large as Earth. The spacing of the planets, the amount of primordial material that should have been there, everything points to a missing world. Instead, we find fragments. The total mass of every single asteroid, every speck of dust in that entire belt, adds up to less than the mass of our moon. It is a skeleton of a region, as if someone took a fully formed planet and removed 99.9% of its substance, leaving behind only the scattered crumbs. This is not a story of emptiness, but of profound loss. It's a tale of what might have been, of planetary dreams shattered not by a cataclysm, but by a gravitational tyranny that began in the earliest days of our sun's family. To understand what went wrong, we must travel back in time, to the very beginning. Picture the infant solar system, not as a place of orderly planets, but as a swirling, chaotic disk of gas and dust, the solar nebula, rotating around our newborn, furious sun. In this nebula, The process of world building began with the most delicate of steps. Microscopic particles of dust, silicate and metal began to stick together through static electricity. Gentle collisions allowed them to grow from specks to grains, from grains to pebbles, from pebbles to boulders. This was the first act of accretion. But there was a formidable barrier, the meter-size barrier. Objects around a meter in diameter faced a cosmic catch-22. They were too large for static forces to hold them together efficiently, but too small for gravity to take over as the dominant binding force. Worse, they experienced intense drag from the nebula's gas, causing them to spiral inward toward the sun on a timescale of centuries, far too quickly to ever grow into a planet. It was a puzzle that threatened to halt planetary formation everywhere. The solution is one of the most elegant mechanisms in all of astrophysics: the streaming instability. Imagine a murmuration of starlings, where thousands of individual birds create beautiful, flowing patterns through simple, local interactions. The streaming instability works in a similar, self-organizing way. As solid particles drifted through the gas disk, they created subtle ripples and pressure variations. These variations, in turn, influence the motion of other particles, creating a feedback loop that concentrated scattered dust into dense, coherent filaments. These filaments could reach densities thousands of times greater than their surroundings. And when they became dense enough, gravity finally awoke. These filaments collapsed under their own weight, fragmenting into the first true planetary building blocks, planetesimals. These were not loose piles of dust, but gravitationally bound objects kilometers to hundreds of kilometers across, cosmic seeds with the potential to become worlds. In the region between Mars and Jupiter, this process worked beautifully. The stage was set. The raw materials were abundant. The streaming instability created a thriving population of planetesimals. Computer simulations suggest this primordial asteroid belt may have contained several Earth masses of material. They followed peaceful, circular orbits and collided at gentle, productive velocities, sticking together, growing larger. A planet was not just possible here, it was inevitable, or so it seemed. Because growing in the outer solar system, feasting on the abundant ices and gases beyond the frost line, was a behemoth, Jupiter. As it accreted mass, it became not just a planet, but the gravitational sovereign of our system. Its influence began to stretch across empty space, reaching into the belt region like the hand of a giant. Its gravity, subtle at first, began to perturb the orbits of those growing planetesimals. The gentle, circular dances became elliptical and chaotic. The crucial change was in the speed of collisions. Where before, objects had bumped and merged, now they slammed into each other. There is a critical velocity threshold for any material, a few hundred meters per second for rock. Below it, collisions build. Above it, collisions destroy. Jupiter's gravitational stirring pushed the collision velocities in the belt well above this threshold. The environment flipped from a nursery to a battleground. Planet formation didn't just slow down, it switched off. The process of accretion was replaced by the process of erosion. But Jupiter's role was far more active, far more dramatic than simply stirring from a distance. Recent, groundbreaking research reveals that Jupiter didn't just watch from its orbit. It went on the move. It migrated. This is the heart of the grand tack hypothesis. In the early solar system, while still embedded in the gaseous disk. Jupiter's gravitational interactions with that disk caused it to spiral inward. It moved from its birthplace, around 3.5 astronomical units from the Sun, to as close as perhaps 1.5 AU, deep into what is now the inner solar system. Imagine Jupiter as a cosmic wrecking ball on a slow, inevitable path. On this inward journey, it plowed through the very region where that fifth terrestrial planet was trying to form. The effect was not a gentle stirring, but a catastrophic scattering. Planetesimals were flung in all directions. Some hurled into the inner solar system, some ejected outward, some cast into the Sun. The belt was not just excited, it was eviscerated. But the story doesn't end there. Saturn, growing to maturity, eventually caught Jupiter in a gravitational resonance. This resonance reversed their migration, sending both giants back outward. On this return journey, Jupiter encountered a different population, primitive, carbon-rich, water-bearing planetesimals that had formed in the frigid realms beyond its original orbit. These objects were scattered inward. Some found stable orbits in the outer parts of the now devastated belt region. This double migration had a profound and lasting effect. It explains the most puzzling feature of the modern asteroid belt, its compositional diversity. The belt we see today is not the original population. It is a cosmic refugee camp. The asteroids near Mars are predominantly S-type, dry, rocky, and metallic, similar to the material of the inner terrestrial planets. These are the survivors that originated closer to the Sun. But as you look further out in the belt, you find increasing numbers of dark, carbon-rich C-type asteroids, objects brimming with water, locked in clay minerals. These are the refugees from the outer solar system, scattered inward during Jupiter's grand migration. It is as if you took the ingredients for a cake from separate shelves, threw them into a single bowl, and gave it a mighty stir. The belt is that bowl, a mixed archive of materials from across the entire early solar system. This mixing is our key evidence. It tells us that a dramatic, large-scale reshuffling event must have occurred. The peaceful formation of a single planet from local materials could never have created such a blend. The gravitational hand of Jupiter, moving through the raw materials of the infant system, is the only force powerful enough to have done it. So, we begin with a mystery, a missing planet. We have a prime suspect, Jupiter, and we have a motive, the fundamental dynamics of a growing giant in a gaseous disk. The evidence is scattered across millions of orbits. What we must do now is examine that evidence in exquisite detail to understand not just the crime, but its profound consequences for Mars, for Earth, and for the very possibility of our existence. The early solar nebula was a place of gradients and boundaries, where temperature and chemistry shifted dramatically with distance from the violent young sun. Close in, the heat was so intense that only the most refractory materials, metals, and certain rocky silicates could remain solid. Everything else was vaporized. But further out, beyond a critical boundary called the snow line or frost line, temperatures dropped sufficiently for volatile compounds like water, ammonia, and methane to condense into ice. This wasn't just a minor change. It was a fundamental shift in the available building materials. Inside the snow line, you could only build rocky worlds. Outside it, you could build rocky icy cores, massive enough to then capture vast atmospheres of hydrogen and helium to become gas giants. The asteroid belt region, in its primordial state, sat intriguingly close to this boundary. It was a frontier zone, with access to both the dry rocky materials drifting outward from the inner hot zone and the abundant icy materials condensing in the cold just beyond. From a compositional standpoint, it was the perfect place to build a unique, perhaps water-rich terrestrial world. A world that could have been a sibling to Earth, but different. The journey from microscopic dust to planetesimal is a story of overcoming immense statistical odds. After the streaming instability created those first gravitationally bound clusters, the true growth began through pairwise collisions. In the inner solar system, where the terrestrial planets formed, this was a slow, hierarchical process. Planetesimals collided and merged, forming moon-sized to Mars-sized planetary embryos. These embryos then, over tens of millions of years, engaged in a final violent dance of giant impacts to assemble Mercury, Venus, Earth, and Mars. In the asteroid belt, this process started with equal promise. The planetesimals there were numerous and massive. They had the right composition, the right orbits, and, it seemed, the right environment. For perhaps the first million years, growth proceeded. Objects like Vesta, which we will meet in depth later, were not just forming. They were growing large enough that internal heat from radioactive decay began to melt their interiors. They were on the path to becoming differentiated protoplanets, worlds with metallic cores, rocky mantles, and basaltic crusts. They were, in every sense, planetary embryos. The asteroid belt was not a backwater. It was a thriving construction site for what should have been the fifth terrestrial planet, possibly even the largest of them all. But Jupiter's influence was a slow-acting poison in this environment. Its gravitational perturbations did more than just make orbits elliptical. They created what dynamicists call velocity dispersion. Essentially, the planetesimals, all initially on similar circular orbits, began to move at different speeds and in different directions. When the velocity dispersion is low, collisions are gentle mergers. When it is high, collisions become hyperbolic smash-ups. Jupiter relentlessly pumped up this dispersion. The transition point is subtle but absolute. For two rocky planetesimals, if their relative collision velocity exceeds roughly 500 meters per second, the energy of impact is more than enough to overcome their mutual gravitational attraction and the material strength of the rock itself. Instead of merging, they shatter. Jupiter pushed the average collision velocities in the belt well past this threshold. The environment crossed a phase boundary, from a state of growth to a state of erosion and fragmentation. This wasn't a single dramatic explosion. It was a slow, grinding depletion that played out over millions of years. Large planetesimals would collide and break into families of smaller fragments. These fragments would then collide with others, creating even smaller debris. It was a collisional cascade, but the truly devastating effect was ejection. Jupiter's gravity, especially during its hypothesized grand tack migration, didn't just break things apart, it threw the pieces away. Computer simulations are crystal clear on this point. When you model the early solar system with a migrating Jupiter, the primordial asteroid belt is stripped of 99.9% of its mass in a shockingly short astronomical time frame within the first few million years. The material met various fates. Some was flung into the outer solar system to become part of the Kuiper belt or to be ejected entirely into interstellar space. Some was hurled sunward, contributing to the late heavy bombardment that scarred the inner planets. A tiny fraction, less than 0.1%, remained in stable orbital niches, just beyond the reach of the most violent resonances. This is the first origin of our present-day belt, a skeletal remnant of a once thriving population. Then came the second act, implantation. As Jupiter migrated back outward with Saturn, its gravitational field swept through populations of planetesimals that had formed much further out, in the region between and beyond the giant planets. These were the primitive bodies, rich in carbon, organic compounds, and water ice, the C-type asteroids. Many of these were scattered inward. Some found themselves placed on stable orbits in the outer regions of the depleted belt. Meanwhile, some of the rocky S-type planetesimals from the inner solar system, perhaps those that had formed in the terrestrial planet zone but were not incorporated into Venus or Earth, were scattered outward by the same gravitational chaos, finding homes in the inner belt. This is how the modern belt achieved its stratified composition. It's not a native population. It's a collection of immigrants. The inner belt is dominated by dry, rocky refugees from the hot inner system. The outer belt is dominated by dark, watery, carbonaceous refugees from the cold outer system. The boundary between them is a mixing zone, a testament to the efficiency of Jupiter's gravitational mixing. This grand narrative explains more than just the belt. It solves several solar system puzzles at once. Take Mars. The red planet is small, about half the size of Earth. Yet it formed in a region where, based on the density of the primordial disk, there should have been enough material to build something much larger. Why is it so puny? The Grand TAC model provides an elegant answer. When Jupiter migrated inward to around 1.5 AU, it plowed through the very region where Mars was accreting. Its gravity acted like a massive plow, scattering the planet-building material away from Mars's orbital feeding zone. Mars was left to form from the leftover scraps, stunted in its growth. Earth and Venus, forming closer to the Sun inside Jupiter's inward migration limit, were relatively spared this scattering and could grow to their full size. Furthermore, this mixing and scattering delivered crucial materials to the inner planets. The water in Earth's oceans, the organic molecules that may have seeded life, these almost certainly came not primarily from comets, but from these water-rich C-type asteroids that were scattered inward during the giant planet migration. Our world, our very biosphere, is in part a product of this ancient gravitational upheaval. The asteroid belt, therefore, is not an irrelevant collection of space rocks. It is the archived record of the process that made our solar system look the way it does. It is the key to understanding why we have small Mars, why we have water on Earth, and why there is no planet between Mars and Jupiter. Its story is our story. And to read that story, we must learn the language of the asteroids themselves. We must become forensic scientists, examining the evidence they have sent to us, quite literally, falling from the sky. To understand the scale of the cosmic crime, we must examine the survivors, the largest witnesses to Jupiter's gravitational tyranny. These are not mere rocks. They are frozen chapters of a history that never fully unfolded. Chief among them are Ceres and Vesta, the belt's most massive residents. Their stories, read through the lenses of telescopes and spacecraft, reveal two dramatically different fates for a would-be planet. One, a preserved relic of the outer solar system. The other, a stunted, differentiated proto-world. Let's begin with Ceres, the largest object in the asteroid belt, now rightfully classified as a dwarf planet. It contains nearly a third of the belt's total mass, a solitary giant among fragments. For centuries, Ceres was just a faint point of light. But the Dawn spacecraft's arrival in 2015 revealed a world of profound surprises. Its surface, mottled and cratered, held a stunning secret. Bright, reflective spots scattered in its craters, most prominently in a crater. Spectral analysis revealed these were not metallic deposits, but vast expanses of sodium carbonate, a salt. This was the telltale residue of briny water that had erupted from within Ceres and sublimated into space, leaving the salts behind. The implication was staggering. Ceres was not a dry, inert rock. It was, and likely still is, a geologically active world, with a subsurface reservoir of liquid water, a cryovolcanic remnant of a once warmer interior. But here lies the first major clue to its origin. Ceres's overall composition is all wrong for where it currently resides. It is rich in water-bearing clay minerals and ammonium salts. Ammonia, in particular, is a key marker. It only condenses at extremely low temperatures, far from the sun. Ceres's chemical fingerprint screams that it formed not in the relatively warm inner solar system, where it now orbits, but out in the frigid realm beyond Jupiter, perhaps between Jupiter and Saturn, where ammonia ice was plentiful. It is a classic C-type body, but on a massive scale. Its very presence in the middle of the asteroid belt is powerful, direct evidence of the Grand Tack migration model. Ceres is not a native of the belt. It is an immigrant, a refugee. It formed in the outer solar system as a large, icy plainstimul. Then, as Jupiter and Saturn migrated, their gravitational tides swept Ceres inward, depositing it in its current orbital home. The fact that it survived this traumatic journey mostly intact is a testament to its size and strength. Its subsurface ocean, if it still exists, is a sealed capsule from that ancient cold birthplace. Ceres tells us that the outer belt is populated by scattered giants, and that water, in vast quantities, was a passenger on this cosmic relocation. Vesta, the second largest asteroid, tells a completely different but equally revealing story. Where Ceres is dark, primitive, and water-rich, Vesta is bright, evolved, and dry. Dawn's visit to Vesta painted a picture of a miniature planet that had lived a full and violent geological life. Its surface is dominated by basaltic rock, the product of ancient lava flows. Most dramatically, two massive overlapping impact basins at its south pole, the Rhea Silvia and Venonea basins, scar its surface, evidence of catastrophic collisions that nearly destroyed it. But the most important revelation was Vesta's internal structure. Detailed gravity measurements confirmed what meteorites had long hinted. Vesta is differentiated. It has a dense metallic iron-nickel core, overlain by a rocky mantle, and topped with a basaltic crust. This is the classic structure of a terrestrial planet: Mercury, Venus, Earth, Mars. Vesta is not a pile of primordial rubble. It is a protoplanet, a planetary embryo that was on its way to becoming a full-fledged world. Vesta's existence is the second crucial piece of evidence for our detective story. It proves that the asteroid belt region did have the material and the conditions to begin forming a real planet. Vesta itself was a contender, a growing embryo that successfully melted and differentiated within the first few million years of the solar system, heated by the decay of short-lived radioactive isotopes like aluminum-26. But then, its development was frozen in time. It never grew to planetary size. Why? Because Jupiter's gravitational stirring turned the region from a nurturing environment into a destructive one. The collisions that Vesta endured were were not the gentle, accretionary bumps needed for growth, but violent, shattering impacts. The Ria Silvia Basin is the scar from one such event, which ejected so much material that we have a whole family of smaller asteroids, the Vestoids, and meteorites on Earth that came from it. Vesta survived, but battered and stunted. It is the fossil of a process that was abruptly terminated. Its differentiation tells us the belt was once massive and active enough to create planetary interiors. Its battered state and small size tell us that process was shut down prematurely. The timing is critical. Vesta differentiated before the belt was violently stirred. Jupiter's disruptive influence came not at the very beginning, but after the first generation of planetary embryos had already formed. The belt story is one of arrested development, not a failure to start. These two survivors, Ceres and Vesta, bookend the narrative of the belt's composition. One is an imported, primitive, water-rich world from the outer system. The other is a native, evolved, dry world from the inner system. Their coexistence in the same broad region of space is impossible to explain without a massive solar system-wide reshuffling event. They are the anchor points for the gradient of material we see across the belt, from the S-type, Vesta-like asteroids in the inside, to the C-type, Ceres-like asteroids on the outside. But the evidence is not limited to these two giants. It rains down on us. To find the next set of clues, we must look not up into space, but down at the ground, at rocks that have traveled from this ancient battlefield to our very doorstep. Meteorites are the universe's gift to planetary detectives. They are free samples, delivered across hundreds of millions of kilometers of space, of asteroids we may never visit. Each one is a time capsule, preserving within its crystalline structure the chemical and physical conditions of the solar system's first few million years. When scientists began analyzing them in detail, they expected to find a relatively uniform composition, reflecting the average stuff of the solar nebula. What they found instead was a bewildering diversity, a diversity that tells the same story of scattering and mixing that Ceres and Vesta do. The most direct link we have is with Vesta itself. A class of meteorites known as head meteorites, Howardites, Eucrites, and Diogenites have spectral fingerprints that match Vesta's surface perfectly. Eucrites are basaltic lavas that float on Vesta's surface. Diogenites are crystals that settle deep in its mantle. Howardites are breccias, rubble created from the impacts that scarred it. We hold in our hands pieces of this distant protoplanet, and by dating them radiometrically, we know Vesta's crust solidified within just 2003 million years of the solar system's formation. This is incredibly fast, and it confirms that large melting bodies existed in the asteroid belt region almost immediately. Other meteorites tell stories from further afield. Carbonaceous chondrites are the most primitive meteorites we have. They are dark, full of carbon, water-bearing minerals, and even microscopic diamonds and pre-solar grains that predate our sun. They have undergone almost no thermal processing. They are essentially samples of the original solar nebula, compacted into rock. Their chemistry is unmistakable. They formed in the cold, outer solar system. Yet here they are, falling on Earth. Their presence in our collections is another direct testament to the inward scattering of material from beyond Jupiter. Some even contain amino acids and other complex organic compounds, showing that the chemistry of life's building blocks was active on these ancient, water-rich asteroids. Then, there are the iron meteorites, chunks of almost pure nickel-iron alloy. These are the cores of differentiated asteroids that were shattered by collisions. They are the shattered hearts of failed planets, Vesta-like embryos that were torn apart in the belt's violent grinding mill. The diversity of these meteorites, from the differentiated irons and heads to the primitive carbonaceous chondrites, is impossible to explain if the asteroid belt was just a quiet local construction zone. This diversity requires a solar system that mixed its ingredients violently and thoroughly. This mixing is further confirmed by the study of asteroid families. When a large asteroid is shattered in a collision, the fragments don't just fly off randomly. They retain similar orbital elements, their paths around the Sun cluster in specific patterns. By identifying these clusters, or families, astronomers can trace the debris back to a single parent body. The Vesta family is the clearest example, but there are dozens of others. Some families are very young, only a few million years old. Others are ancient, dating back to the earliest days of the belt. The existence of these ancient families tells us that the high-velocity, destructive collisions predicted by the Jupiter-stirring model have been happening for billions of years. It also tells us that the belt's population is not static. It is continually being remade by catastrophe. The size distribution of objects within a family, how many large fragments versus how many small ones, acts like a forensic report on the impact that created it, revealing the parent body's strength and the collision's violence. All of this evidence from survivors, meteorites, and families paints a consistent picture. But our detective work must also account for the emptiness, the haunting gaps in the belt itself. If you map the orbits of main belt asteroids, you find they are not smoothly distributed. At certain precise orbital distances, there are sharp drops in population, the Kirkwood gaps. These gaps occur at orbital resonances with Jupiter. For example, an asteroid at about 2.5 astronomical units from the Sun would orbit exactly 3 times for every 1 orbit of Jupiter. An object in this 3.1 mean motion resonance gets a regular, periodic gravitational tug from Jupiter at the same point in its orbit. Over thousands of cycles, these tugs add up, systematically stretching and twisting the asteroid's orbit, increasing its eccentricity until its path crosses the inner solar system, or it is ejected entirely. These gaps are not absolute voids. They are dynamic drains. They are the ongoing signature of Jupiter's dominion, still actively clearing the belt today, 4.5 billion years after its formation. The asteroids we see are those that have managed to avoid these resonant death traps, finding stable orbits in the sheltered zones between them. The very architecture of the belt, its clumps and its gaps, is a direct imprint of Jupiter's gravitational influence, a fossilized tidal pattern in a sea of rock. So we have our mechanism and our evidence. But a good detective must also consider alternative scenarios. What if the Grand Tack model is wrong? Other theories exist. The empty primordial belt model suggests that perhaps the region between Mars and Jupiter never had much material to begin with, and the current asteroids are all implanted from elsewhere. While this accounts for the compositional mixing, it struggles to explain the existence of large differentiated natives like Vesta. Vesta clearly formed in situ. It's not an implanted object. Its differentiation requires it to have been part of a locally abundant population that provided the radioactive heat. Another model, the chaotic excitation scenario, proposes that Jupiter and Saturn's orbits evolved into a temporarily chaotic configuration, violently exciting the belt without large-scale migration. This could also deplete the belt and mix populations. The debate continues, driven by ever more detailed computer simulations and data from missions. However, the Grand TAC model's power lies in its ability to explain multiple solar system puzzles: the belt's mass and composition, Mars's small size, the delivery of water to Earth, with a single, elegant sequence of events. It is the leading theory because it fits so much of the evidence. Yet, the story doesn't end with formation. The asteroid belt is not a static museum exhibit. It is a dynamic, evolving system where the processes that shaped it continue to this very day in slow motion, and these ongoing processes are the final piece of our investigation. The asteroid belt we see today is not the final state of that ancient drama. It is a snapshot in an endless, slow-motion ballet of destruction and renewal. The same forces that shaped it, gravity and collision, continue to sculpt its population, grinding it down, shifting its members, and occasionally hurling a fragment toward the inner solar system. To understand this ongoing evolution, we must meet two subtle but powerful characters: the Yarkovsky effect and the Yorp effect. These are non-gravitational forces, gentle nudges born from nothing but sunlight, that over millions of years can steer the fate of mountains. The Yarkovsky effect is a masterpiece of subtlety. An asteroid absorbs sunlight on its day side, heating up. As it rotates, this warm region moves to the night side, where it radiates the heat back into space as infrared photons. Photons carry momentum. The key is that this re-radiation is not perfectly symmetric. The warmest point is slightly offset from the point that received the most direct sunlight. This creates a tiny net thrust, like a faint rocket engine. For a house-sized asteroid, this force is infinitesimal, 1 billion times weaker than Earth's gravity. But over 10 million years, it can change the asteroid's orbit by tens of millions of kilometers. The direction of the push depends on the asteroid's rotation. For a prograde rotator, spinning the same way it orbits, the Yarkovsky effect causes a gradual drift away from the Sun. For a retrograde rotator, it drifts toward the Sun. This effect is size-dependent. It's most effective on asteroids between about 10 meters and 10 kilometers in diameter. Smaller objects are blown around by solar radiation pressure. Larger objects are too massive to be moved significantly. The Yarkovsky effect acts as a slow, persistent conveyor belt, moving mid-sized asteroids through the belt over geological time, gradually feeding them toward the powerful gravitational resonances with Jupiter. Once in a resonance like the 3-1 Kirkwood gap, their orbits are rapidly pumped up into planet-crossing trajectories. This is the primary delivery mechanism for near-Earth asteroids and the meteorites that reach our planet. It connects the slow thermal physics of a spinning rock to the dramatic events of impact craters and shooting stars. The related Yorp effect, Yarkovsky-O'Keefe-Radzievsky-Paddock, deals with rotation rather than translation. Sunlight reflecting off and thermally radiating from an irregularly shaped asteroid can exert a net torque, causing its spin to speed up or slow down over time. The Yorp effect can explain why we see so many small asteroids rotating so rapidly, some with periods of just a couple of hours. In extreme cases, it can spin a rubble pile asteroid, a loose collection of fragments held together by gravity, so fast that centrifugal force overcomes its weak self-gravity, causing it to shed material or even split in two. This is thought to be a primary mechanism for creating binary asteroid systems, where a primary asteroid is orbited by a smaller moon created from its own shed debris. These binaries are common, and they serve as natural laboratories for measuring asteroid masses and densities, revealing their internal structure. Many asteroids, particularly the larger ones, are now understood to be rubble piles, not solid monoliths. This is a direct result of the collisional environment of the belt. A solid rock, when hit hard, shatters. A rubble pile can absorb the impact energy by rearranging its fragments. It is more resilient. The prevalence of rubble piles is an adaptation to a violent neighborhood, an evolutionary outcome of billions of years of collisions. And those collisions continue today. While the era of planet-smashing giant impacts is long over, the belt remains a shooting gallery. High-velocity impacts between asteroids at speeds of several kilometers per second are common on geological timescales. These collisions create new asteroid families, refresh surfaces, and generate the cosmic dust that pervades the inner solar system. Sometimes, we catch these events in real time. Astronomers have observed asteroids suddenly sporting comet-like tails, not from sublimating ice, but from clouds of dust ejected by recent impacts, or from rotational breakup. The asteroid 6478 Gault, for instance, was seen with twin dust tails in 2019, likely caused by material being gently shed as it spun apart due to the Yorp effect. These active asteroids blur the line between asteroids and comets and show us that the belt is not a quiet place. It is a place of continuous, if slow motion, activity. All of these ongoing processes, Yarkovsky drift, URP spin-up, collisional grinding, act as a slow leak, gradually depleting the asteroid belt over time. The resonant gaps with Jupiter are the main drain pipes. Current estimates suggest the belt is losing mass at a rate that would halve its population over a timescale of hundreds of millions to billions of years. This means the belt was slightly more massive in the past, though never remotely close to its primordial mass before Jupiter's intervention. This slow depletion is balanced, in a way, by the continued breaking apart of larger asteroids, which replenishes the population of smaller fragments. The belt exists in a quasi-steady state, a dynamic equilibrium between creation, through fragmentation, and destruction, through ejection. It is a system that has achieved a kind of stability, not through stillness, but through a constant balanced flux. This brings us to the final, and most personally resonant, connection: the delivery chain from the asteroid belt to Earth. The near-Earth asteroids, NEAs, that occasionally make headlines are the current end products of this multi-stage process. They are fragments that were first created in the main belt, then slowly drifted via the Yarkovsky effect into a gravitational resonance, were rapidly kicked into an Earth-crossing orbit, and now whiz by our planet as potential hazards and opportunities for study. The meteorites that land are the lucky fragments that survive this journey and atmospheric entry. By studying the cosmic ray exposure ages of meteorites, how long they've been traveling as small objects in space, we can trace their delivery timelines. Most have been in space for a few million to tens of millions of years, confirming that the process of launching material from the belt is continuous and ongoing. We are, in a very real sense, living inside the fallout zone of this ancient and still active celestial conflict. The dust from asteroid collisions rains down on Earth constantly as micrometeorites, tens of thousands of tons per year, carrying with it the same chemical stories that the larger meteorites do. We breathe in atoms that were once part of the asteroid belt. The connection is not just historical, it is continuous and intimate. But to grasp the full cosmic significance of this story, we must step back and see how the asteroid belt's fate is inextricably linked to the most profound question of all. How did we get here? The story of the asteroid belt transcends a mere celestial curiosity. It is a foundational chapter in the story of our own existence. The gravitational machinations of Jupiter that sculpted the belt did not occur in isolation. They fundamentally configured the inner solar system, setting the stage for a very specific kind of planet to emerge in the habitable zone, our Earth. Let's connect the final dots. We've seen how Jupiter's grand tack migration likely stunted Mars's growth, leaving it small and geologically quick to fade. But what about Earth? When Jupiter plowed inward, it also scattered material from the outer solar system, water-rich, carbonaceous material, directly into the feeding zones of the growing terrestrial planets. Earth, accreting in this newly enriched environment, could incorporate these precious volatiles. The water in our oceans, the carbon in our biosphere, the nitrogen in our air. A significant fraction of these essential elements were likely delivered by these scattered asteroidal immigrants. Without Jupiter's migration, Earth might have been a dry, volatile, poor rock, more like a larger version of Mercury. The asteroid belt, in its role as the scattered remnant of that process, is the leftover evidence of this crucial delivery. This idea is powerfully supported by isotope geochemistry. Scientists can measure the ratios of different isotopes of hydrogen, oxygen, and nitrogen in Earth's water and air, and compare them to those found in different classes of meteorites. The isotopic fingerprints of Earth's water match most closely with those of carbonaceous chondrite meteorites, the ones that come from the outer asteroid belt, from asteroids like Ceres. Cometary ice, by comparison, often has a different deuterium to hydrogen ratio. While the debate is nuanced and likely involves multiple sources, the evidence points strongly to water-rich asteroids as the primary delivery mechanism for Earth's oceans. The asteroid belt, therefore, wasn't just a casualty of planetary dynamics. It was the warehouse, and Jupiter's migration was the delivery truck for the ingredients of habitability. Furthermore, the organic compounds found in carbonaceous chondrites, amino acids, sugars, and nucleobases show that complex prebiotic chemistry was not only possible but widespread in the early solar system, occurring naturally within the warm, wet interiors of these primitive asteroids. When these asteroids struck the early Earth, they didn't just bring water, they brought a starter kit of organic molecules. They were not necessarily seeding life directly, but they were certainly stocking the primordial pantry with the essential ingredients. The asteroid belt, in this light, becomes a cosmic chemical factory whose products were essential for life's emergence. Its formation story is thus a prerequisite for our own. This narrative also transforms our perspective on exoplanets. As we discover thousands of planetary systems around other stars, we see an incredible diversity of architectures. Hot Jupiters orbiting close to their stars, systems with multiple planets in tight resonances, and debris disks of varying shapes and densities. Our own solar system, with its clear separation of small rocky planets inside and gas giants outside, and its prominent asteroid belt, is just one possible outcome. The Grand Tack model explains why our system looks this way. It tells us that the migration of giant planets is probably a common phenomenon in young stellar systems. The presence, size, and composition of asteroid belts or debris disks in other systems can thus serve as a diagnostic tool, telling us about the migration history of their giant planets and, by extension, the potential for water and organic delivery to any terrestrial worlds in their habitable zones. Understanding our asteroid belt is the Rosetta Stone for interpreting these distant systems. Finally, the asteroid belt endures as a frontier. It is a natural laboratory for studying the fundamental processes of planetary formation and collision, a resource depot for future space exploration, and a historical archive of unparalleled value. Missions like NASA's Psyche, destined for the metallic core of a protoplanet, will probe the very heart of a differentiated asteroid, telling us more about the building blocks of planetary cores. Sample return missions from primitive asteroids like Ryugu and Bennu are bringing back uncontaminated pieces of the early solar system to our labs. Each mission, each observation, adds another sentence, another paragraph to the story we've been piecing together. As we approach the end of this cosmic investigation, we see the asteroid belt not as a failure, but as a testament to the dynamic, often violent, processes that shape planetary systems, a testament to the delicate balances of timing, of location, of gravitational influence that determine whether a region of space becomes a planet or a relic field. The fragments between Mars and Jupiter are the enduring witnesses to the gravitational tyranny of Jupiter, the stunted dreams of planets like Vesta, and the long migratory journeys of worlds like Ceres. They are the scattered pages of a story that explains the size of Mars, the water of Earth, and the very chemistry of life. Their silent, endless dance is the permanent record of our solar system's most formative era. And as we look up, or as we hold a meteorite in our hand, we are touching that history, connected across the void by the same forces that once gathered stardust into worlds, and in our case, into a world that could look up and wonder about it all. Let us now delve into the very fabric of the belt today to see how its current, dynamic state is a direct legacy of its violent birth. The asteroid belt is not a uniform swath of debris. It is a highly structured, finely tuned ecosystem governed by celestial mechanics. The most striking features are the aforementioned Kirkwood gaps, those empty zones carved by Jupiter's resonant gravity. But between these gaps lie safe havens, stable islands where asteroids can persist for billions of years. These are often associated with weaker resonances or locations where several gravitational influences from Jupiter and Saturn cancel out. The largest population of asteroids, for instance, is found in the inner belt, relatively untouched by the strongest resonances. This intricate architecture is a fossilized force field, a map of gravitational power from 4.5 billion years ago that still dictates traffic today. Within these stable zones, asteroids have sorted themselves into families and spectral types with remarkable order. The inner belt, warmed by the sun and dominated by S-type, siliceous asteroids, is where we find the vestiges of the original local planet-forming material, the dry, rocky stuff. Moving outward, past a transition zone, we enter the realm of the C-type, carbonaceous asteroids in the middle and outer belt. This is the domain of the immigrants. Beyond them, hugging the outer edge near Jupiter's influence, are the mysterious and dark P-type and D-type asteroids, even more primitive and possibly rich in organic tars, likely originating from the far reaches of the solar system. This compositional gradient is the smoking gun for large-scale transport. It's as if the solar system's ingredients, once separated on a vast cosmic shelf, were violently shuffled, and then allowed to settle roughly by density, with the heavy, dry rocks sinking inward and the lighter, icy carbonaceous material floating outward, all within the vast bowl of Jupiter's gravitational influence. The physical evolution of individual asteroids adds another layer of complexity. Space weathering, the constant bombardment by solar wind particles, micrometeorites, and cosmic rays, slowly alters the surfaces of these airless bodies. Over millions of years, it darkens and reddens the spectra of silicate-rich S-type asteroids, making them look more like the primitive C-types. This means our telescopic census has a bias. We might misidentify an old, weathered S-type asteroid as a C-type unless we look with very precise spectral tools. This weathering process connects the belt to every other airless body in the solar system, from Mercury to the moons of Mars to distant Kuiper Belt objects. By studying it on asteroids, we learn to read the surface ages of worlds across the solar system. Collisional evolution continues to be the great recycler. The size distribution of asteroids, the fact that there are few large ones and exponentially more small ones, follows a predictable pattern established by a collisional cascade. Large bodies are broken down into smaller ones, which are broken down further, all the way to dust. This cascade has been running for so long that the belt's population is largely in a steady state for objects below about 100 kilometers in diameter. The very largest, like Ceres and Vesta, are survivors that have dodged catastrophic disruption through luck, location, or sheer strength. But even they bear the scars. The constant rain of impacts grinds down surfaces, creates regolith, asteroid soil, and churns the outermost layers in a process called impact gardening. An asteroid's surface is a palimpsest, with the records of ancient impacts buried or erased by more recent ones. This makes the task of the cosmic detective challenging. The evidence is constantly being eroded, yet within that erosion is its own story, the story of an active, living belt. The discovery of binary and even triple asteroid systems has opened a fascinating subplot. How do these form? The leading theory for many is the Yorp effect. As sunlight spins up a rubble pile asteroid, material can be shed from its equator. This shed material, if it doesn't escape entirely, can coalesce into a small moon under its own weak gravity. Other binaries may form directly from the reaccumulation of debris after a gentle disruptive collision. These binary systems are nature's gift packages. By observing the orbital dance of the two bodies, astronomers can directly calculate the system's mass. Combined with size estimates, this gives us the asteroid's bulk density, a crucial number. A low density reveals a porous rubble pile structure. A high density suggests a more solid, metallic, or stony composition. The prevalence of low-density rubble piles confirms that catastrophic disruption and reaccumulation have been central to the belt's evolution. This brings us to the immediate human connection, the near-Earth asteroids, NEAs. These are the fragments that have recently, in astronomical terms, been nudged out of the main belt via the Yarkovsky effect and resonant kicks, and are now on orbits that intersect Earth's. They represent the ongoing output of the belt's dynamical machine. Studying their composition tells us about their source regions in the main belt. Their orbits tell us about their delivery pathways, and their physical properties, whether they are solid monoliths or fragile rubble piles, are of paramount importance for the future, both for planetary defense and for potential resource utilization. The OSIRIS-REx mission to to Bennu and Hayabusa 2 to Ryugu revealed both asteroids to be incredibly fragile rubble piles, almost like cosmic gravel heaps held together by microgravity. This fragility is likely common, and it changes how we might need to interact with such objects, whether to deflect a hazardous one or to mine a valuable one. The belt, therefore, is not a relic. It is a system in gentle, constant flux. It is a cosmic hourglass, with the fine sand of dust and small fragments slowly trickling through the resonant bottlenecks, destined either for the sun, for a planetary impact, or for ejection into interstellar darkness. The larger chunks tumble and spin, their orbits gradually shifting under thermal forces, their surfaces slowly darkening under relentless space weathering, waiting for the next collision that will remake them once more. This is the quiet contemporary chapter of a story that began in thunderous violence. And it is a story that continues to write itself across the emptiness between worlds, a perpetual monument to the dynamic universe we inhabit. We have journeyed from the swirling dust of the nascent solar nebula to the gentle, sun-driven drift of mountain-sized rocks. We have seen how the gravitational whim of a giant planet can dictate the fate of worlds, preventing one from forming, stunting another, and scattering the building blocks of life across the inner solar system. The asteroid belt is the enduring testament to this history. But as our investigation concludes, we must synthesize this knowledge into a final, holistic understanding of our place in this cosmic drama. The asteroid belt is more than its fragments. It is a relationship. It is the relationship between order and chaos, between construction and destruction, and between the distant past and our living present. Consider the profound elegance of the timeline. Within the first million years, planetesimals formed. Within 2 to 3 million years, Vesta melted and differentiated. Within 5, 10, or 10 million years, Jupiter had likely completed its grand tack migration, shredding the primordial belt and scattering its material. The terrestrial planets finished their main accretion within 50-100 million years, incorporating the water and organics delivered by that scattering. The late heavy bombardment, around 500 million years later, may have been the final act of clearing leftover debris, some of which was perturbed by the giant planets settling into their final orbits. The asteroid belt we see today is the product of that first, rapid, decisive epoch. Its entire character, its mass, its structure, its composition, was locked in place within the solar system's first 1%. The subsequent 4.5 billion years have merely been a slow, meticulous working out of the consequences, a gradual erosion of the statue whose shape was carved in a brief moment of violent sculpting. This perspective changes how we view our solar system's stability. The harmonious clockwork of planetary orbits is not a given. It is the outcome of a turbulent adolescence that could have resulted in many other configurations. We live in one particular version of solar system history, one where Jupiter's migration happened just so, at just the right time, and moved by just the right amount. In other versions, perhaps Jupiter migrates too far inward, ejecting Mercury, Venus, or Earth. Perhaps it doesn't migrate at all, leaving a massive planet where the belt is, and a dry, barren Earth. Our specific, habitable reality appears to hinge on a series of celestial contingencies, with the asteroid belt as a key piece of evidence for that sequence. As you reflect on this, consider again your connection to this story. The iron in your blood was forged in the core of a massive star that died before our sun was born. but the water that flows through your veins and the carbon-based complexity of your very cells may have taken a more scenic route. That water and those organic molecules might have condensed on a dust grain in the cold outer solar nebula, been incorporated into a growing planetesimal beyond Jupiter, were then violently scattered inward during the planet's migration, wandered for eons in the asteroid belt, were finally delivered to early Earth by a fragment knocked loose by the Yarkovsky effect and a gravitational resonance, and survived the impact to become part of our planet's hydrosphere and biosphere. You are not just a bystander to this story, you are a product of it. The asteroid belt is not just out there. Its history is woven into the fabric of our world and of ourselves. This understanding also frames our future. The asteroid belt is a museum, but it is also a quarry. It contains the raw materials of planets, metals, water, organics, in accessible, near-weightless locations. Understanding its composition and dynamics is the first step towards someday utilizing those resources. More immediately, understanding the delivery mechanisms of NEAs is crucial for planetary defense. The same pathways that brought life's ingredients also bring existential threats. By studying the belt, we learn to map the channels of celestial commerce and hazard. Finally, as we look outward to the galaxy, the asteroid belt becomes a diagnostic tool. When we point our telescopes at distant stars and see debris disks, the telltale infrared glow of warm dust, we are likely seeing the aftermath of their own dynamical upheavals, their own asteroid belts in different stages of evolution. Some may be pristine and massive, indicating quiet systems without migrating giants. Others may be warped and clumped, signaling the gravitational hand of unseen planets. Our asteroid belt is the template, the one we can study up close, that teaches us how to interpret these faint, distant signals. It connects our single data point, our solar system, to the grand statistical sample of the cosmos. So, as we end our 4.5 billion year journey tonight, let the asteroid belt settle in your mind not as a meaningless void filled with rocks, but as a central character in the epic of our solar system. It is the scar of a gravitational battle, the refugee camp for cosmic material, the mixing bowl for life's ingredients, the source of both danger and opportunity, and the silent, orbiting archive of our origins. Its fragments are the scribes, and their language is chemistry, dynamics, and impact craters. We have learned to read that language, and in reading it, we have discovered a story of astonishing violence, delicate balance, and profound connection. A story that tells us how we came to be on a small, wet rock, gazing with wonder at the starlit graveyard of possibilities that made our existence not just possible, but inevitable. The dance continues, the fragments turn, and the story, forever unfinished, spins on in the dark.